1963, at the southern end of Iceland, a volcano emerges from the sea. New land rises out of the Atlantic Ocean. In 1991, the volcano Pinatubo in the Philippines erupts and buries the surrounding land under meters of ash. 1995, a devastating earthquake destroys parts of Kobe, a city and industrial center in Japan. Our Earth is a restless and turbulent planet. Over and over, it is shaken by earthquakes and disturbed by volcanoes. But not all regions on Earth are equally affected by these natural disasters. Earthquakes and volcanic eruptions stretch out across the planet, like, for example, the Pacific Ring of Fire. They appear along young mountain ranges, such as the Rift Valley in eastern Africa. They also traverse the Atlantic and South Pacific Oceans. Earthquakes and volcanic eruptions occur at weak points in the Earth's crust. These weak points of activity define sections which rub against each other. These sections are called plates. The theory of plate tectonics is about the dynamic movements of the Earth's crust. These plates are by no means confined by the coastlines of the continents. They extend into the oceans as well. The 8 main plates are the Eurasian and African plates, the North and South American plates, the Nazca plate, and the Pacific plate. The Australian Indian plate, and in the south, the Antarctica plate. By looking deep into the Earth, we can begin to understand the theory of plate tectonics. Our planet is made up of different layers. The core is a mixture of solid and liquid metal. The mantle is a mass of hot liquid rock circulating in currents around the core. These thermal convection currents are the force driving the movement of the plates. The outermost part of the Earth's mantle and the exterior crust forms the lithosphere. This lithosphere, or crust of rocks, is divided into plates. When molten rock rises up out of the convection currents, the lithosphere arches, stretches, and finally bursts open. A plate has ruptured. Molten rock pushes up through a crack to the surface. Dissolved gases are released, shooting lava high into the air, and the crack widens to form a rift valley. Such a rift valley extends right across Europe, from the Mediterranean Sea to the North Sea. It is here that the Eurasian plate started to break up, some 40 million years ago. Part of this fracture zone is the Upper Rhine Valley. A subsided rift is concealed under the wide valley floor. Its flanks are marked by the Vosges to the west, and to the east by the famous Black Forest. An extinct volcano called the Kaiserstuhl sits in the middle of the rift. Africa also shows signs of physically splitting apart. Numerous active volcanoes mark a zone of expansion, the Great Rift, where the African plate is dividing. This rift is so far advanced in the north that it plunges beneath the Red Sea. These hydrothermal vents are evidence of plate movements still in progress. In millions of years, the Red Sea could expand so much that it becomes an ocean, similar to the Atlantic. Around 200 million years ago, the Atlantic Ocean began to form. Hot rising magma pushed America and Africa apart. As the magma cooled, it welded onto the edges of the continental plates, which were moving apart. In this way, new plate matter builds up on the spreading ocean floor, and the Atlantic grows a few centimeters each year. The cleft, where magma rises up from the depths of the earth, is marked by a long submerged mountain range, the Mid-Atlantic Ridge. It surfaces at only one spot, Iceland. Here the cleft is visible, where two plates, the Eurasian and the North American, are spreading apart. Frequent volcanic eruptions in Iceland are evidence of the ongoing process of the sea floor spreading in the Atlantic. Geologists discovered that oceanic plates can be pushed under continental plates. Because oceanic plates are heavier than continental plates, they dive deeper and deeper into the mantle of the Earth until they melt down. Magma, rich in gases, is generated along the top of the sinking plate. It rises to the surface and triggers intensive volcanism, sometimes unleashed in explosive eruptions. Along such subduction zones, we find the most dangerous fire spitter on Earth, Mount St. Helens in the U.S. In 1980, its summit disappeared in an enormous explosion. With continuing subduction, the oceanic plate is constantly drawn down into the mantle and melted. Now we see the edges of two continental plates moving towards each other until they collide. The subduction is coming to a standstill because the continental plates are both too light to be pushed down into the mantle. The edges of the plates wedge into each other and are pushed up by enormous pressure to form mountains. The highest mountain range on Earth, the Himalayas, formed in this way. So far, we have seen that plates can separate in spreading zones or overlap in subduction zones. But they can also slide past each other. Here, the Pacific plate slides past the North American plate a few centimeters a year. The boundary of these transformed plates is marked by a deep chasm, the San Andreas Fault. This movement doesn't occur without friction. The plates constantly lock into each other until the increasing force is released by huge jerking earthquakes. San Francisco is built on this trembling, dangerous ground and pays a high price. In 1906, the city was totally destroyed by an earthquake and the fires that followed. A similar disaster hit again in 1989, burning suburbs, flattening buildings, and destroying bridges. The San Andreas Fault shows clearly that all plates are in constant movement. In the millions of years of Earth's history, this activity has changed the position and appearance of the continents. The German meteorologist and physicist Alfred Wegener was the first to write about continental drift. In 1915, his book, The Origins of Continents and Oceans, was published. He concluded from the geometric matching of African and South American coastlines that these continents must have been a single landmass once. Fossils of a small reptile found only in South America and South Africa. And imprints in clay of plants with the same leaf types. Also evidence of a long-lasting glaciation and similar rock formations are apparent on both continents' southern parts. What Wegener didn't know was that continents don't move alone. Wide areas of ocean floor move with them. Modern science has made it possible to follow the movement of plates into prehistorical times. We are going back in time some 300 million years. In this time, Africa and America, together with all other landmasses, formed a supercontinent called Pangaea. "200 million years ago, Pangaea started to break apart. The North American plate broke off and the Atlantic started to open up in its northern region. Then, in its southern region, as the African and South American plates drifted apart. India also moved away from Pangaea and migrated northwards. The oceanic part of the Indian plate submerged under the Eurasian plate. Eventually, the continental part of the Indian plate collided with Asia. This led to the uplifting of the Himalayan mountain range. Meanwhile, the African plate reached the southwest of the Eurasian plate. The continents pushed into each other, and mountains around the Mediterranean Sea began to form. This process of mountain building is still going on. A few millimeters are added to the European Alps each year. The theory of plate tectonics serves as a master key for understanding the history, structure, and dynamics of the Earth's crust. It explains how mountains form and oceans grow. Plate tectonics make us aware that the face of our planet is in constant change.